Well, I think we can get started. So good afternoon, everyone. Welcome to ethics seminar series. And this is our last seminar this year. And this is John. I'm the seminar coordinator, and I'm together with Miss Kathy Medley. She's our communication specialist. So Kathy and I will be this moderator. And we are also glad that our associate director, Ralph Ferrero, joined us today. Just so you know that the seminar is being recorded, and the video will be later published on our YouTube channel. So please feel free to check out, and you can ask us, bring up any questions after the presentation. You can either chat us or you can unmute yourself and bring up an Google question. And we are very excited that the speaker will give away his new book today. Before he gets started, I will let our communication specialist, Kathy, to talk about this. Kathy, please go ahead.
Hi, everyone. So Professor Delsole is giving away one copy of his new book, which is out this month. It's called Statistical Methods for Climate Scientists. And to enter to win, you go to go.umd.edu/Delsole book. I put it in the chat if I said it too quickly. So it's a quick Google form. You can fill it out up until the end of the seminar. And then at the end, stick around for the Q&A. I'll announce who wins. Okay, so Ralph, you can introduce our speaker now.
Okay, yes, just real quick before I introduce our speaker, I just want to thank John and Kazi, and I think Mark's on there as well for doing such a great job with the seminars this fall, and look forward to more of the same in the spring. So our speaker is he's a professor at the Department of Atmospheric, Oceanic, and Earth Sciences at George Mason University, and also a senior research scientist at COLA, which is the Center for Ocean, Land, Atmosphere Studies. And George Mason is a partner in the our CSIS grant. So it's nice to hear from our partners. And as his title states, I mean, his research focuses on the weather and climate interactions and changes from various time scales. He's been a key contributor to the IPCC Intergovernment Panel on Climate Change, and well published. And as Kazi mentioned, he's got a book, and he also is a co-chief editor for the Journal of Climate. So with that, I'll turn it over to Tim, and let's hear his interesting talk.
All right, thank you. And thank you for inviting me. It's a shame that with the pandemic, I can't come there in person, but I appreciate this opportunity to talk about the work I've been doing. And I'm going to talk about this question of how do we decide if models are realistic? And this is work I've been doing in collaboration with Michael Tippett. So just to introduce this topic, I'm going to show some climate indices, the AMV index. Actually, I forgot to ask, can you see my cursor? Because my talk relies on that.
We can see it if you don't move it like too frequently. But right now that's like the perfect speed.
Okay, fantastic. Thank you. Sorry, we should check that first. But anyway, so what I'm showing here is an AMV index from 2 model simulations. And by the way, it doesn't matter what index I'm using. The question I'm going to ask is very broad, and I'm just using the AMV index as just an example. So the top 2 curves are the AMV index from 2 model simulations from GFDL and HadGem. And then this bottom curve in the black is observations. And the question we have is whether the models generate time series that are consistent with observations. Now, because these are simulations, it's not a forecast, so we can't do anything like compute a correlation or compute a mean square error because these are independent time series. So what we're really asking is whether the statistics of the time series are consistent between models and observations. So your first order statistic is the mean, so you can ask are the means the same? Well, if you know much about climate models, you know that the models have serious biases, and almost any measure of a difference in means will tell you the models are inconsistent. But yet we derive a lot of value from these models, and we often just subtract out the model climatology whenever we compare to observations. So we're a very forgiving human race. We're going to forgive mean biases and go on to other statistics. So the things I will talk about in this talk don't concern differences in means. So the next statistic you might think of is variance. And so the question would be, is the variance from a model simulation equal to the variance in the observations? And the standard test for doing that is the F test, which you may have learned if you took statistics. But there's a problem. The F statistic assumes that the data is independent. But you can tell from looking at these time series that they're zero-correlated, which means that if you know the value at one time, you have a pretty good idea what it will be at the next time just because of persistence, because these curves are fairly smooth. So that means because of the serial correlation, your standard test for differences and variances can't be applied here. And in fact, most of the standard tests that you're familiar with, assume independent data. And so they can't be applied to this question of whether you have consistent statistics between models and observations. So that's really the focus of my talk. Okay, so now I'm not able to advance. Here we go. So the central question I'm going to be examining here is, how do you compare serially correlated time series? So many of you are probably thinking the first thing you might think of is power spectra, is to compute a power spectrum and compare them. So here I'm just showing a random figure that shows the AMV, the power spectra of the AMV index for several different models. Those are all the different colors. And this thick dashed black curve is some sort of red noise model fit. And so the question is, based on this power spectra, and by the way, there's no observations here, but you could still pretend one of these curves is observations and ask, are the models consistent with each other, or are they consistent with one of them if you select them to be observations? So based on this curve, or based on this figure, you would not be able to answer that question of whether they're consistent because there's no uncertainty estimates in this. So if you were to put in uncertainty estimates, you would have something like an error bar that would show a confidence interval. And here I'm just showing an example with those two time series I showed in the beginning. So here's the power spectra of observations in black and two model simulations. And then we have a confidence interval. So now that we have this uncertainty, now you can look at this and try to get some sense of whether they disagree. And you can see that maybe the biggest difference here is, let's just say that it is bigger than this confidence interval. That by itself would not be enough for you to say that these power spectra are different, because we cherry picked it, right? And by the way, you could imagine at a certain frequency by random chance, they would exceed this standard, standard error. So what we really need is a test that looks at the entire spectrum and then gives us a single decision of whether the power spectra are consistent with each other. So there are such tests, and there's a paper by Coates and Diggle in 1986, so it's pretty old, which showed how to do this. They derive several tests for this and compared them. The basis of these tests is a bit clever. They rely on the fact that if two power spectra are equal, then the ratio ought to be a constant. But if you have a constant power spectra, that's just white noise, and there are already tests, spectral tests of white noise. So the idea is, which is kind of clever, is you can adapt these tests for white noise and use them to this problem of testing this question of whether two power spectra are equal or not. So this test, some of these tests were looked at in this paper by Robert Lund and his group, and when he applied this to climate type data, he found that these tests have low statistical power, which means that only large differences in the spectra could be detected. So for our kinds of problems, they weren't really effective. before I explain why they have low statistical power, there's another approach you might think of, which is to compare autocorrelation functions. So here's a figure I was able to find from a publication that shows the autocorrelation function of the AMV index based on several models. And then this thick yellow curve is showing the autocorrelation from observations. And so you can still ask the question, are these models consistent with observations? Well, still, again, you cannot really make a judgment based on this because you don't know what the uncertainties are in this figure. We do have these two dashed lines here, which is a significance level that's typically put on the autocorrelation function, but that is just testing if the correlation is different from 0. That's not the question we're asking here. We're asking, are the differences in the autocorrelation significant? And moreover, we want to look at all the autocorrelations to come up with a single decision about whether they're consistent or not. So again, Robert Lund in this paper, which I highly recommend. I learned a lot from this paper. I think it's a pretty nice paper. He and his group developed a test for this equality of autocovariances. But when we applied that to our data, we found that one step of this is you have to estimate a covariance matrix, and that estimate was not positive definite, which means you couldn't evaluate the test because you had to take an inverse of a matrix. And so because of that, the test is not reliable. Like there are times when you can't actually apply it. So back to this question of why they have why these tests have low statistical power. One issue is that the power spectra that we get in climate have a very distinctive shape. They tend to be red noise models, by which I mean that they tend to be maximum at low frequencies and then just decay after that. Whereas these tests that have been developed in the statistical literature have not made any assumptions about the structure of the power spectra. And that's kind of important for a broad range of applications. So for instance, speech recognition gives you a very different power spectrum. And so you want to test of whether you can detect the difference between two people talking. But here in climate, we tend to find only red noise spectra, or maybe one bump somewhere. And so we want to test it sort of constraints. If you're able to constrain the shape of the power spectra, then you may be able to derive a more powerful test. And so the approach we took is to just fit the data to an autoregressive model. So an autoregressive model will take the present value of a process and represent it as a linear combination of the past values. And then you add a constant, and then you add noise. And so when you collect all those parameters, you have these v parameters, you have this gamma and this sigma x, so there's a total of p plus 2 parameters. So once you specify those parameters, you've specified that process. And then if you have another time series y, you set up another autoregressive model, and then and it has its own coefficients. And then the idea is that if those coefficients, if all the parameters in one model are equal to all the parameters in the other model, if 1-to-1, then you have the same process. And so we would say that they are statistically indistinguishable. So that's really the idea, is we're fitting the time series to two separate models, and then we're asking if the coefficients are the same. So just to be really clear about what I'm testing, my null hypothesis is that the phi parameters are equal, and then the variance of the noise process here are equal. And then the alternative hypothesis here is that at least one of these parameters differs. Notice I didn't include these gamma parameters. These gamma parameters appear in these equations. And it turns out those parameters control the mean. And I've already explained that I'm not interested in changes in the mean, so we want to leave those out from the test. So now, once you specify an ARP, an autoregressive model, that completely specifies the autocorrelation function and the power spectra. So when we say that there's an equality of AR models, that implies you're going to have equal autocorrelation functions or equal spectrum, power spectra. So if two time series could have come from the same AR model, then I'm going to say that they're statistically indistinguishable. So now to derive a test for that, we use the likelihood ratio test, which is just a standard procedure for deriving test statistics. And it ends up giving you a statistic that looks like this, which is the log of this combination of variances. And these variances are estimates of the noise in these autoaggressive models. So the sigma x, which I've written out here, it's an estimate of the variance of this error model. And then there's an estimate for the y variable. And then there's a third estimate of the variance, which you can derive assuming the null hypothesis is true, which means assuming all these parameters are equal, you get another estimate of the variance. And so when you set up that ratio, and take the log of it, that's the test statistic. And then there are, of course, some degrees of freedom you have to account for. Now, you can't tell from the way I've written this, but if the variances are the same and the phi parameters are the same, then this d becomes 0. And then if there's any difference in these parameters, it becomes positive. So that means because of those two properties, it has a property of a distance, right? Because if the two AR models have exactly the same coefficients, then this d is 0. And then if there's any difference in any of those parameters, and it doesn't matter which direction, then this d is positive. So it has the attributes of a distance. So I can use this d, which I'm going to call the deviance, to measure the difference between two AR models. Now, if you were to derive the likelihood ratio test for just variance, not these AR models, but just variance, you would actually get the same kind of ratio, except these would be the actual variances, not these variances of the autoregressive models. And that's an important departure from how this test goes compared to other tests. To estimate that variance, what you do is you take the present value and you subtract off all the AR part of the model. So these are the phi parameters in this gamma. You subtract that off. And so in a sense, what we're looking at is the residuals from this model. And then we're looking at the variance of those residuals. And it turns out that even if you start out with a time series that's highly serially correlated, by the time you remove this predictable part, you end up with the residuals that are mostly white noise. So that's really the key departure in the way this test approaches data versus other tests, in that we do something called a pre-whitening transformation. We first try to make the data look more white, and then after it looks white, then you can use these standard F statistics and other things. So I'm going to show an example of this. I'm going to stick with the AMV index. This is defined as the annual mean SST averaged over the Atlantic between 0 to 60 degrees. I'm going to look at pre-industrial control simulations from CMIP5. Pre-industrial control means these are simulations where there's no year-to-year variability of the forcing. So that means all the variability comes from internal variability. And for observations, I'm going to look at this 165-year period from ERSST v5. Now, of course, in observations, you have both internal and forced variability. So to do this comparison, we want to take out the forced part. So for that, what I'm going to do is just take out a second-order polynomial in time to remove the forced part. Now, I'm totally well aware that this is a controversial point. There's no universal agreement on how you should remove the forced part, especially for the North Atlantic. But what I can say is that I've explored different approaches, and that's not really the point of my talk. So I'm just going to focus on just using this second-order polynomial to remove the forced part. And I can say that all of my broad conclusions at the end it doesn't depend on the way I took out the forced part. Another element is that although I'm assuming that it's an autoaggressive model, I didn't say what the order was. So we will select that using something called Akaki's information criterion, or it's a corrected version of that. And if you apply it to the CMIP5 models, it ends up selecting p equal 1 for most of the models, but not all. So now this is kind of a tricky point, but in this context, if you choose too high an order, well, of course, that means overfitting, and that's a problem for prediction. But overfitting is not a serious problem in this study, because if you use too many predictors for your autoaggressive model, that overfitting is taken into account in the test. The downside of using too high an order is that you just use statistical power, that you need a bigger difference in AR models in order to detect it. But that turns out not to be a concern in this study. So although most of them are p equal to 1, if you choose p equal 3, that includes all the models. And so we, in that case, we say it's adequate, that if you choose p equal 3, it will handle the cases where p equal 1 is adequate, but it'll also handle the ones that require AR3. And it turns out only 2 other models would not needed higher order. So you have to bear that in mind. Some models, the AR3 may not be a good fit. So here are the this is the AMV index from all the models that I'm looking at. And the top is the black curve, which is the observations. And so the question we're asking is the model simulation of this AMV index consistent with the observed index? And so just to recap, I'm going to choose a model, fit it to an AR model, and I'm going to choose the observations, fit that to an AR model, and then test if the coefficients between those 2 AR models are equal. So this is the result. The x-axis is showing the models. The y-axis is showing this deviant statistic. This gray line is showing the 5% significance. So anything that's below this 5% significance line means that it's statistically indistinguishable from observations. And you see there's about 1/3 of the models are indistinguishable, whereas 2/3 of the models are different. We decide that there's a detectable difference from observations, with the worst models being the GISS models over here. So for simulations of the AMV, more than half the models are inconsistent with the observations. But I didn't say how they differ, right? I just did the test to detect a difference, but I didn't say where that difference was. But now, since we're comparing models in terms of the AR process, we have to think about the differences in terms of the AR model. And so I'm going to split the AR model into 2 parts. There's the AR parameters, so that's the phi parameters here, and then there's the noise. And then we want to know, is there a difference in other words, when there's a difference, is it because the models differ in the noise? Is it because they differ in these AR phi parameters? Or is it because of both? Now, what does it mean, though, if you say that the noise parameters differ? And I've already mentioned that it means that after you regress out the lag 1 or the lag p behavior, you're asking if the residuals have the same variance. So that's one interpretation. Another one is dynamical. If you think in terms of this AR model, that this is really quantifying the 1-step prediction error. That is, if you were to make any prediction, this would all be your prediction for 1 step, and then this is the error. And so if you find a difference in the noise, you're really saying there's a difference in the 1-step prediction error. On the other hand, the phi parameters, that usually encodes things like the memory and the predictability and the dissipation and the dynamics. So when there's a difference in the AR parameters, we will think of that as a difference in dynamics. Now, it turns out that this deviant statistic can be split into 2 parts. One part measures just the difference in noise, and the other part measures the difference in AR parameters. And so I can at least just plot those to see which of these dominates. So this is summarized here. So the blue is showing the deviance due to the noise, and then the red is showing the deviance due to the AR parameters. And then I have significance levels for each of those with these solid blue and red lines. And then I put a circle across depending on whether the noise is significant or the difference in noise is significant, or the difference in AR parameters is significant or not. So a dot across means it's not significant. So looking at this level, we see maybe half the models are consistent if you look at the noise and AR parameters separately. But over here, you see there's a significant difference, and it's usually because there's a significant difference in noise. So now this says there's just a significant difference in noise, but we don't know which way. Is it too much variance, too little variance? But since it's a simple parameter, it's just the variance, we could just look at the ratio of the variance, the ratio of the noise variance between the CMIP5 model and the observations. So a ratio greater than 1 says there's too much variance in the model, and a ratio less than 1 says there's too little variance. And you see that in most cases, it's the reasons the models differ from observations because they have too little noise variance. And then this is the regression pattern you get when you regress the pre-whitened variable with the corresponding SST pattern. And these all, they strike me as like the tripole pattern, something like that. You don't really get a different pattern if you use the actual variable versus the pre-whitened. So it's not really giving you a different structure, but it's critical for doing this test, or having a threshold for deciding, making a decision whether it's different or not. So now everything I've talked about so far is just the A and B index, one index. So the next level of question is, we know there's more to climate than just one index. What about other indices? And what about the relationship between the A and B and other indices? So here I'm still going to stick with SST, but I would like the A and B to be one of these patterns that I'm talking about. So there's a convenient basis set for choosing this, and that's the eigenfunctions of the Laplace operator. So you probably have not used this. It's a relatively new technique. But the idea is you solve Laplace's equation. You find the eigenvectors of Laplace's equation over the Atlantic domain. And the nice thing about those eigenvectors is they're orthogonal in space. And the first one is the spatially uniform pattern. And the subsequent ones can be ordered by some measure of length scale. So if I were to project data onto this first Laplacian, that would be equivalent to just taking the A and B index, because it's a spatial average over the domain. And then the second Laplacian is orthogonal to the first. And you can see it has this dipole structure, which is measuring the north-south gradient of SST. And the third Laplacian is orthogonal to the first two. And you can see it'll measure the east-west gradient and so forth. And as you go to higher and higher order, you get to progressively smaller and smaller scale. And you can quantify spatial scale. So by the time we've hit 6 or 7 Laplacians, we're around 2,000 kilometers. So the idea is I'm going to take model output, project them on each of these patterns. That will give me time series, and then I'll use those time series to conduct a test. The framework, though, is still the same. I'm still thinking of autogressive, but now everywhere where we had a scalar, we now have vector. So we have a vector here, and now the phi parameters, these AR parameters, now they become matrices. So there's a lot more information here, but the concept is still the same. The concept is I'm still going to fit it to a model of this structure. I'm going to do it twice, once for the model, once for the observations, and ask, are those parameters equal? And it turns out that the likelihood ratio test looks very similar to the univariate case. And the main thing is that everywhere where you saw a variance, you replace it with a determinant of a covariance matrix. And otherwise, the test looks very similar. But there is a new complication. We had, in the univariate case, we had to choose the order P. But in the multivariate case, we have to choose not only the order P, but also the number of Laplacians. And this question comes up even if you're familiar with linear inverse models. You have to choose the number of UFs. And I forgot to mention that if I choose P equal to 1, then this is equivalent to a linear inverse model. So if you're familiar with limbs, I'm effectively comparing limbs. So this problem of how to choose the number of UFs, this has been around a long time, and Michael Tippett and I have really thought about this for a long time. And recently we came up with a criterion that we're pretty excited about. We call it mutual information criterion. And the nice thing about this criterion is that if you fix the number of Laplacian or fix the number of UFs, then it becomes exactly equivalent to a Kaki's information criterion, which is standard selection criterion. But then if you now allow changes in the number of EOFs or the number of Laplacians, it has very attractive properties that make it a very compelling choice for choosing both the order and the dimension of your model. And it turns out you could also use it to choose the number of EOFs in canonical correlation analysis, which has been kind of a challenge in our literature, that there hasn't been a standard criterion for choosing the number of EOFs in either a linear inverse model or CCA. So we're hoping that people will become familiar with this and actually and use this, and hopefully it will be successful. So it turns out if you use this mutual information criterion, it says that if you choose a first order AR model with 7 Laplacians, that's adequate for most of the models. So the results I'm going to show you is based on that, 7 Laplacians with first order. So here's the result of this deviance statistic. X-axis showing each of the models. The y-axis is showing the deviance. This gray line is the significance, and so everything below here is insignificant. And you see there's one model here that's insignificant. So in other words, indistinguishable from observations. That's CMCC. And I've also included observations here where I'm splitting the data in half, and I didn't describe that in the beginning, but I'm doing some tricks here, which I'll get to in a minute, where I'm splitting things in half to do some tests. But otherwise, you see that all the other models are inconsistent observations, and with the biggest discrepancies seen in the GISS models. So by including smaller scale variability in addition to the AMV index, we find that virtually all the models are unrealistic or not consistent with observations. Now, it's been known that if you run these GCMs long enough, you can observe epochs where there are periods where the variability seems to change over long periods of time, like a century or so. So here's an example from a paper by Wittenberg, looking at the Nino3 index. And you see, here's an example of a Nino3 index, and you see there's a certain amplitude here. But then if you go to a different multi-decadal period, the amplitude is very different, and so forth. And so one question that could come up is whether if we were to take time series from the same model, would this test say that they're different? They came from different models, even though they didn't. So to do that, to test that, what I'm going to do is take all of these time series and just split it in half. And then I'm going to compare the first half of each of these with the second half of everything else. And the idea is that if I compare a time series from the same model, the first and second halves from the same model, those differences ought to be small. Whereas if I compare a time series for the first half for one model and a different model for the second half, those differences should be large. So is that what happens? So this is the result of that. The models that I'm using for the first half are on the x-axis here. The models on the second half are on the y-axis. And then I'm showing the value of this deviance statistic, and the shading represents significance. So there's a lot of structure here. I don't expect you to absorb it immediately. The first thing I would like you to sort of focus on is look at the diagonal. The diagonal is where you're comparing a model with itself between the two halves. And what you see is that along the diagonal, there are no shaded boxes. So that means there's no significant difference between a time series from the same model. So there's no epochs in this time series, which is admittedly short. The second thing to notice is that you do find agreement even across models, and they occur in these kind of clusters, which I've sort of helped see here. So here's a box of 4 models that are indistinguishable from each other, and you see they're all the GISS models. And you see that pattern repeats, that if you have a model from the same institution, they tend to have relatively small differences. So just to guide you, here are the GISS models here, and if you were to look at this and swap the first and second halves and compare them, it would be pretty hard to tell which came from which model. So that's consistent with our visual interpretation. But it holds for other modeling centers. So if we go to CMCC, there's a cluster here where they're similar. The GFD models are also grouped together. CNRM is grouped together. Over here is a bigger block. These are the NCAR models, which also happen to be grouped with the NOR ESM models. And here's the access models and so forth. So what this says is that models from the same institution tend to agree more closely with each other than they do with observations. And this is a result that has been reported in other ways. But what's kind of nice here is that we have a very rigorous criterion for deciding whether they match or not. So although I'm able to detect a difference, I haven't said anything about where that difference is. So the next question is, how do they differ? And in contrast to the univariate case, they can differ in many different ways in the multivariate case. So we can still split up our AR model in terms of the noise and the AR parameters. So we think of the noise, which is the unpredictable part, and then the AR parameters, which is kind of capturing the predictable part. And we can ask, are the differences that we do see that's mapped out here, Is that because of the noise, or is it because of differences in the dynamics? So again, we can split up the deviance in terms of difference in noise and difference in parameters, and those end up being independent of each other. You can test them separately. And so this is the result of what happens when you look at this vector autoregressive model with 7 Laplacians. So again, the blue is the noise, the red is showing the AR parameters, and the red and blue lines are showing the corresponding significance levels. So anything below these lines is insignificant. And so this dot and cross says that these are the only 2 things that are insignificant or indistinguishable from observations. And so everything else is distinguishable. But now we can see that the source, the primary source for that is in the noise, that the blue tends to exceed its significance level, especially over here, that most of the differences between models and observations is due to having a different noise. Now again, I say that there are different noises, but I haven't said how the noise differs. Is it because they have different patterns? Is it because the amplitudes are off, or what? So that's a more complicated question, but yet that's the question, is that what we're effectively saying when there's a significant difference in noise is that the covariance matrix for the residuals of this AR model differ across the 2 data sets. And so now we're actually asking, how do you quantify difference in matrices, which is a much more difficult problem. So the approach we used here is basically something like EUF analysis, is that we find a linear combination that optimizes differences in noise variances. And if you do that, it ends up being equivalent to maximizing a ratio of variances. And the nice thing about that is that when you do that, you get a complete set of components, and those components end up decomposing this deviant statistic into independent terms. And this procedure is called, or at least we've been calling it, covariance discriminant analysis. There's not actually a formal name for this. And you can think of it as generalizing principal component analysis or EUF analysis to describing differences in covariance matrices. After all, an EUF is just an eigenvector of a covariance matrix. And here, we're thinking of this generalizing to 2 covariance matrices and describing their differences. So when I evaluate that, just like with the EUF analysis, you get eigenvalues, and here I'll get 7 eigenvalues, and each one of those is a component that explains this noise. And so I'm plotting the most extreme values and joining them by a line just to help guide that by eye. So I'm plotting the maximum eigenvalue and the minimum eigenvalue, and so that is showing the linear combination. Given a linear combination, we're finding a linear combination that gives the maximum ratio of this ratio of variance, and then over here would be the minimum ratio of variance, and these dashed lines are showing the significance level. So if this line is totally within these 2 dashed or dotted lines, then there's no significant difference in the noise. So you have to have a line that goes across the dashed line in order to say that you have a significant difference in noise. And when the ratio is greater than 1, we know that there's more variance in the model than in observations. And if the ratio is less than 1, there's too little variance in the noise compared to observations. And you can see in most cases, the reason that there's a difference in noise is because there's too little variance in the noise. So now you can do a regression pattern on these components. So if we look at the ones that have too much variance, this is what that regression pattern looks like. And you see there's a common story here. It says that there's too much variance in this pattern that tends to be localized in the North Atlantic. And then you can do the same thing by looking at these components that have too little variance and then finding the regression pattern. And that's what these patterns look like. And I have to confess, I spent a lot of time trying to interpret these patterns, but I eventually gave up. You might say that there is some commonality across models from the same institution. So here are 3 patterns for the GITS models, but that's not always the case. I wouldn't say that like these NOR ESM patterns are the same. So we found these patterns a bit difficult to interpret, but at least, I guess another point to make here is that these percentages here is quantifying the percentage of the deviance that can be explained by this one pattern. So in this GIST model, 50% of all the deviances in the noise can be explained by this one pattern. So although it's difficult to interpret, it is telling you, it's something that you might be able to lock onto and you might be able to tune or whatever. The next question though is if there could be a difference in the noise. Let me go back to the equations. So I just looked at how to diagnose differences in noise. So next we want to look at how do we diagnose differences in the AR parameters, and that's much more tricky. And so just to be clear, when we find that there's this deviance statistic for the parameters is significant, that means that at least one of these elements of this matrix differs by a lot, by enough to describe a difference between the models. So now, the real question here that we struggled with is how do you describe this? Like, do you show the matrix elements? You know, we spent a lot of time trying to think of ways that would be insightful in describing a difference in these matrices. And so our first thing was let's just repeat the same trick we did before, take a linear combination and find the combination that maximizes that statistic. And again, when you do that, it decomposes that deviance into a sum of terms. And it takes a little bit of ingenuity to figure out that ultimately that's equivalent to performing a generalized signer value decomposition of the difference in AR parameters. So you may have heard of optimal perturbations or SVD for a limb model and so forth. So it's very similar to that, but there's an important difference, which is number one, we're not doing SVD of the limb operator if it's AR1. We're doing an SVD of the difference. And the second point is it's generalized because the standard SVD assumes a Euclidean norm, and you may not actually be thinking that you're dealing with a norm, but actually you have to specify a norm. And here, in order to get this decomposition to work out, you have to choose those norms very specially, very particular. And if you choose them right, then it exactly decomposes this deviance statistic. And it turns out that by doing that SVD, you're finding the initial condition that maximizes the difference in response in the VAR model. And so we think this is kind of an interesting and new approach to diagnosing model errors. And we're calling this difference in dynamics SVD because we're looking at the difference in these AR parameters, which encode the dynamics. So when you perform this SVD, you get the singular values, which quantify the magnitude of this difference. So these are what the singular values look like, the leading singular values. And then this dashed line is showing significance. And so there's only about 5 models that show significant difference due to these AR models, due to the difference in dynamics. So that sort of confirms the picture we were sort of seeing before, is that the biggest differences between the models is due to this difference in noise, but there are a few models that also seem to have different dynamics compared to observations. So now just to illustrate how this difference in dynamics SVD works, is that when you perform the SVD, you get an initial condition. And so I'm showing that initial condition here. It's the same for the 2 models. Then you take that initial condition and you operate it on the model's AR parameters. So for the HADGEM model, you take those parameters, operate it, and that gives you a prediction for the next step. And that's what I've plotted here. And then you take the same initial condition, but now then you use the observation estimated AR parameters to make a prediction. That's the prediction I'm showing at the bottom right. And what you see is that if you look in the southern end of this domain, that those patterns look very similar. But if you look at the northern end, the extreme northern end, there's a big difference in the amplitude. And what you can see is that in the observation is that warm anomaly gets damped, it gets damped, whereas in the HADGEM model, it tends to persist for a year. So and the idea is that this SVD is finding the initial condition to make this difference in the 1-year prediction as big as possible. So this seems like a pretty interesting way to diagnose models. Another example, instead of the HADGEM, which was the biggest one, is the third one, the MyRock model. So again, we redo this SVD, and here I'm applying the initial condition, but it's different now. And we take this initial condition, operate it on the MyRock model AR parameters to make a prediction. That's shown here. And then to do the same thing for observations. And here's the pattern based on the observation model. And you can see for the observations, it just takes the pattern and tends to dampen it. Whereas in the MyRock model, you actually get a different sign in the North Atlantic compared to observations. So there's something going on in the dynamics here that is causing a reversal in this warm anomaly. That's a lot of material I think I've covered. I've probably overwhelmed some people. So I thought it was best not to go too overboard. So I'm going to stop there, and I'll just summarize now what I think I've just showed you. So first, I've proposed a rigorous method for comparing simulations and observations that accounts for correlations in space and time. And what emerges from here is a deviant statistic, which you can use to measure a difference in these processes. So you could use it to rank models based on their closeness to observations. I discussed a new criterion called mutual information criterion, which can be used to select the lag and the number of variables. And you could also use it for choosing the number of EOFs for a limb model, for instance, or the number of EOFs you use in CCA, canonical correlation analysis. I've applied it to annual mean North Atlantic SST, and I finally, or eventually conclude that virtually all the models are unrealistic after you include small scale information. And then I've shown some discrimination techniques that can be used to optimally diagnose differences in the noise statistics and differences in the AR parameters. And this difference in the SVD, difference in dynamics SVD shows that some of the climate models produce one-year predictions with entirely the wrong sign over large spatial scales. And then all these results have been written up, and they're published in a series of papers in this journal, Advances in Statistical Climatology, Meteorology, and Oceanography. Now, I've covered a lot of new material, mutual information criteria, discrimination. And if you're not familiar with this, I have news for you. There's a new book out written by myself and Michael Tippett, where we try to explain these things. And this is based on a course I've been teaching for over a decade. And so if you want to learn more about it, that's where I can direct you. So with that, I'll stop here, and I'm ready to take questions.
Thanks, Professor Delsole. So if anybody has any questions, you can go ahead and, I said raise your hand in the chat, but no, you don't have to do that anymore. You can just unmute yourself and ask a question. But before you do that, keep your questions in your head for a second, because I'm going to announce the giveaway winner. It's always a little bit weird. Here's my drum roll. So congratulations to In-Seong Jiang. I hope I pronounced that correctly. You provided your Mail account to us, so we will just connect you with the publisher so you can get your free book. So congratulations, In-Seong. So Michelle Leroux, you raised your hand, so you can go ahead and start off the Q&A section.
Hi, Tim. Very nice talk. Definitely a lot of interesting nuggets in there. So I can't help to notice that when you showed the maps with the components with too little noise variance, I'll let you get there, that it's not true for all of them, but for most of them, I would argue you get a little bit of a tripole pattern. It can vary in sign, obviously, but I find that interesting because there is literature that discusses the Atlantic tripole pattern, which is thought to be kind of an SST response to like NAO variability and such. So I was wondering if you considered that as a possibility that maybe these models are just not, able to get that signal, or rather that variance as well.
Yeah.
As in the observations.
Yeah, I would agree with you. That's definitely some of these, I think you would kind of peg as the tripole pattern. And so I think it is saying that the tripole pattern has too little variance. And I agree with you. There are studies that have already said that. So we're showing results that are consistent with that. But there are, I would be hard pressed to say that this is the tripole pattern maybe, or this is the tripole pattern. So maybe if you squint your eyes. So I wouldn't say it's the dominant difference. So that's one point, is that the tripole could be in all of these. It could be off in all of these, but here I'm maximizing for the biggest differences. And so it may not project exactly on the tripole.
Yeah. Okay. Thank you so much.
Yep.
Mike Evans also has his hand up. Mike, you can ask your question too.
Yeah, hi Tim. Thanks for this talk. Sorry, I came in about 10 to 12 minutes late, so I may have missed the answer to my question. So all of this work you've focused on ocean surface temperature, right?
Right, right.
Okay.
The examples I've shown, yes.
Okay, well, that's, I guess, what I'm going to ask about. So that, of course, has a lot of built-in persistence to it. And then, like, we have only so many data points to be able to define things like autoregression and higher order autoregression. So have you applied the same techniques to atmospheric variables, things which, you know, are whiter but are a little bit red, like, you know, think annular modes, maybe in the Northern Hemisphere, to have good long data series. What do you find? Are the models still like deficient in terms of amplitude of variance and persistence? Thanks.
Yeah, good question. Short answer, I have not done that. So I really, you're right though, in that I was keen on choosing a variable where serial correlation was strong, because that was sort of the problem, is I wanted to answer the question, how do you compare data where you have a strong serial correlation? Now, of course, if the data does not have strong serial correlation, these methods should still work too. And in fact, if you set these V parameters to 0, then these tests reduce to standard tests. And believe it or not, people still have not done that test precisely. So I actually don't know what would happen if I were to take this and use atmospheric variables. So that's definitely on my to-do list.
Can I ask another quick one, which is just detail? Is Laplacian technique, is that going to be domain specific?
Exactly, yes. So the nice thing about Laplacians is that, yes, they are domain specific, but in this case, that's an advantage rather than a disadvantage. Most people would use the EOFs, but those are data dependent. So you change your data and then you get a different EOF. Here, as soon as I specify the boundary or the domain, the Laplacians are nailed down. So yeah, as soon as you specify the domain, then you have your orthogonal basis set.
Thanks.
I guess one other thing I want to add to that is that we have codes for that. If you want to use this technique, it's a code that works just like EOFs. You give it the data, but really it's the grid that it needs to see. And it computes the Laplacians and then it projects it on the data. So you can send me an email, or anyone who's listening, if they want to know how to do that, we can point them to the data, to the codes for doing that.
Is
Hi,
anyone else?
this is
Oh.
Liang. Thank you for the talk. So one question is that if we are interested in the pattern of correlation, for example, precipitation temperature, what is the same things can apply to that?
I believe it can. You would just include both of those in this vector autoregressive model.
Okay. So when you do that, then is the test, the criteria, all that could be the same, or we have to create another kind of test?
No, it doesn't matter if the time series you put in here are different variables, but I will emphasize it does assume Gaussian. So if you're talking about precipitation on daily timescales, that probably would not be good enough. But if you're talking about monthly precipitation, it's still non-Gaussian, but you might be able to get away with it. But yeah, it doesn't matter if these are physically different variables, because normally we think of limbs as like one variable, or Matt Newman has been doing SST and height. He's been combining them. And then lately he's had several, soil moisture and other things. So yes, you can put different variables with different units, and the test would still go through.
Great, thanks.
And you don't have to normalize the variables. I guess I'm going to throw that in too. So normally when you do like an EOF analysis, you combine variables, you have to make some artificial rescaling. You don't have to do that here.
That's great.
Does anyone else have any questions? You can unmute yourself, or if you do not have a microphone, you can just type it in the chat and I will read it out loud. Oh, here's a chat question. This is a general question, but how can we help with the development of refinement of models with statistical analysis? Can we use an ad hoc approach with statistics to refine climate models?
So this phrase, refinement of models, I'm going to pick up on that point. So I'm not quite sure I understand the question, but I'm going to try to, I have something to say to that anyway. So here I'm showing the deviance relative to the observations of all the different models. But you can imagine that instead of different models from different institutions, they could be different versions of one model, like you've changed convector parameterization. You could still use this deviance to tell you, did that change in the parameterization make your simulations closer to more consistent with observations or not? So I can see this as a new way of tuning models. You're tuning it to get the right serial correlations, the right statistical properties to match observations.
Great, okay. Oh, Mike, I don't know if you have your hand up again or if you just left it up the first time.
I do, but I defer to someone else who hasn't had a chance. I just have another question.
Okay, we can give them a second. If there's anybody else who has a question, you can go ahead and take your opportunity now. If not, Mike, you're free to ask it.
Okay, Tim, what are the implications for historical reanalysis?
You mean, are you thinking about this forced part?
I guess I'm thinking about like something like a 20th century reanalysis, or dare I say, like things like last millennium reanalysis with paleoclimatic observations. And that's finding consistency between observations and simulations, forced and unforced, given given observational uncertainty and model uncertainty. But what you're saying is like, you can find statistically significant differences in variance and patterns of temporal autocovariance that would be important for, say, applying Kalman filter. And toward the end of your talk, important for using spatial patterns in climate simulations to interpolate from observations back in time. But I think you're just blowing this all up. Discuss.
Yeah. Okay. So there's one question you're asking is, can I use this to compare reanalysis data sets? I think that's one question I heard.
No, I was just asking whether the whole construct of a reanalysis over historical time is broken because you're saying there's disagreement between the observations and what the models would predict.
Oh, okay. Yes. So at least when it comes to SST, or to be precise, North Atlantic SST, is that at the current time, this study says that it depends on how you remove the forced part, but no matter how I do it, I still get the same conclusion that the models are inconsistent with observations in the internal part. And then there's a separate set of literature that's looked at the forced part. Notably, Rong Zhang has looked at this and found that the forced part is also questionable. So it seems like there's hardly anything that the models get right in the North Atlantic if you look at it very carefully. So yeah, we have a long ways to go to get models that are credible simulations of observations.
Hi, Tim. Another question is that, okay, so we know each individual component, each individual variables, it may be not correct some way. Would it be also that some kind of correlation, coherence, for example, just simple surface temperature with sensible heat or latent heat? Is that correlation could be still correct for certain phenomena? Is that the same thing we can apply using the model to find whether this model doing okay?
In principle, yes. So if you are talking about a covariance between variables,
Right.
that would be encoded in the off diagonal elements of these V operators. And Matt Newman has a series of papers where he looks specifically at those to test, is the coupling between variables consistent with observations or not? And so you can adapt this test to do those kinds of questions as well. Here I was asking, are all the coefficients equal? So that would be the coupling and their variances and so forth. But you could adapt this test to look at just the coupling, if that's what you cared about.
Okay, good.
It's a good point. I hadn't thought about that, but yeah, it could be adapted.
Do we have any other questions before we wrap up today? Okay. Well, unless someone interrupts me right now, I think this is the end of our Q&A. Thank you so much, Professor Delsole, for coming to give us this great talk today. Thank you, everybody, for attending. This is our last seminar of the semester. It's bittersweet. We had a great semester. We do have an opportunity for you guys to share your feedback on our seminars, which will help John and I moving forward planning them. One thing that we're talking about is changing the time to better suit everybody's schedule. So please, 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 if you haven't already, we have a Google form. I just pasted it in the chat. It's go.umd.edu/ESSIC-feedback. I'll probably send an email with that as well to all of our ESSIC folks later today. But please give us some feedback on what you liked this semester and what you didn't. And with that, I think that is the end. Thanks, everybody. Have a great day.
Thank you. Bye-bye.
Bye.
Thanks. Bye-bye.
Thank you.